So, what happens when you let an AI write your C++ code? A language that demands absolute surgical precision. Well, you get something that looks right, feels right, but is actually a ticking time bomb. Today, we're diving deep into what I'm calling the C++ vibe coding trap and how AI-generated code can silently fail in some truly catastrophic ways.
Check this out. This quote comes from a real experiment where a company had interns use AI to write C++. And yeah, the code they churned out, it compiled just fine. It looked like legitimate code, but just beneath that surface, it was hiding critical system-breaking failures. And that, right there, is the heart of this entire problem.
The idea behind the experiment was pretty simple. Let's see what happens when a new generation of AI native developers use these powerful code generators to speed up C++ projects. The result? Well, it was basically a masterclass in all the subtle, nasty, memory-related bugs that can bring an entire system crashing down. So let's start our investigation into what went so wrong.
Okay, so the core reason AI gets C++ so wrong is something we can call the syntax mirage. C++ looks familiar, right? It's got the curly braces, the semicolons. It has the same vibe as languages like Java or Python. But that familiarity, it's a total trap.
See, you have to remember, an AI is just a very, very sophisticated text predictor. It's not a compiler. It sees a pattern that works perfectly fine in Java, or a garbage collector automatically cleans up memory, and it just replicates that pattern in C++. The problem? C++ does not have a garbage collector. The syntax looks the same, but the underlying rules of the universe are completely different. The AI is vibe coding. It's writing what feels statistically correct without understanding the brutal reality of C++ memory management. All right, let's dig into our first piece of evidence. This is maybe the most classic trap for anyone coming to C++ from another language, and it's a mistake that AIs make constantly. I'm talking about misusing the new keyword. This just feels so natural, doesn't it? And tons of other languages, you create a new object, and when you're done with it, the system just magically cleans it up for you. But in C++, when you type new, you are making a solemn promise to the computer, a promise that you, the programmer, will personally, manually handle its destruction later. So look at this. We allocate 100 integers with new. But, what if some error happens and the function has to exit early with that return statement? That delete data line, it never gets called. And that memory, poof, it's gone forever. That is a memory leak. And make no mistake, a memory leak isn't just some minor bug. It is a silent killer for applications. Think of it like a tiny dripping faucet inside your computer's memory. Over time, that slow drip can empty the entire reservoir, causing your program or even your whole system to eventually grind to a halt. So what's the right way to do this? Well, the modern C++ fix is a powerful idea called RAII, Resource Acquisition is Initialization. It's a fancy name, but the idea is simple. Instead of raw, new, and delete, you use smart objects, like Studio Vector. This vector handles its own memory. The second it goes out of scope, like when the function ends for any reason, its destructor is automatically called and it cleans everything up perfectly. No leaks, no problem. Okay, our next couple of case files cover two incredibly sneaky bugs. Both of these often lead to the most dreaded error a programmer can see on their screen, a segmentation fault, which is really just a fancy technical way of saying your program didn't just stop, it crashed violently. I mean, this seems totally logical, right? You're looping through a list of things, you find something interesting, and you decide to add a new item right then and there. And while this might work just fine in a language like Python, in C++, doing this is like sawing off the very tree branch you are sitting on. Let's break down exactly how this crash happens. Your iterator, it, is basically a pointer to a specific spot in memory where the vector lives. But when you call pushback, the vector might realize it's out of room. So what does it do? It finds a new, bigger chunk of memory somewhere else, copies everything over, and then destroys the old one. All of a sudden, your original iterator is pointing to a ghost town, to invalid, deallocated memory. The very next time you try to use it, boom, access violation, crash. All right, on to the next culprit. Something called object slicing. This is a big one when you're dealing with polymorphism, with base classes and derived classes. The vibe, especially if you're coming from Java or C#, is that when you pass an object, you're passing the whole object. But in C++, it depends entirely on how you pass it. If you pass a derived object by value to a function that's expecting a base object, the C++ compiler does something brutal.
It literally slices off all the extra data, all the special functionality that makes your derived class what it is, and you're just left with the generic base class part. Any of your custom behavior is just gone. And the crazy thing is, the fix is unbelievably simple, but you just have to know to do it. You add one single character, an ampersand. By passing the object by reference, you're not making a sliced-up copy. You're giving the function a direct line to the original, complete object, preserving its true type and all its special powers. Our final two cases deal with what I like to call ghosts in the machine, data that isn't really there, and pointers that lead to nowhere. Honestly, these are some of the spookiest, most confusing bugs you can find in C++. You know, this one comes from a good place. It's born from a desire for optimization. Copying big chunks of data can be slow, so returning a reference, basically just a pointer to the original data, seems like a really smart move. But here's the catch. It's only smart if the original data is actually still alive. In this piece of code, the variable x is a local variable. It lives on something called the stack, which is basically just temporary scratchpad memory for a function. The very second that function finishes and returns, its entire stack frame is wiped clean. The variable x completely ceases to exist. So the function returns a reference to what exactly? To nothing, to garbage, a ghost. This is called a dangling reference. And trying to use one is like playing Russian roulette with your program. It could crash immediately. It could seem to work while silently corrupting all your data in the background. It's one of the most unpredictable and frankly dangerous things you can do in C++. And finally, our last ghost in the machine. In so many modern languages, if you declare a variable, like a number, it's guaranteed to start at 0. It's a safety feature we just take for granted. But C++, in its relentless pursuit of maximum performance, offers no such safety net. If you just write int counter and do nothing else, that variable doesn't contain 0. It contains whatever random garbage bits and bytes were left over in that specific slot of RAM from the last program that used it. It might be 0, or it might be 10. Or it could be negative 858 million. It's pure chaotic chance, and writing code that relies on it is an absolute recipe for disaster. So, after walking through all of these silent, deadly failures, what's the big takeaway here? It's that when you're working with C++, and especially with AI-generated C++, you can't just be a simple code reviewer checking for typos in style. You have to become a memory auditor. This requires a completely new mindset. You have to start questioning everything. You have to ask, does every single new have a matching delete? Or better yet, am I using RAI to avoid this whole mess? Am I changing a list while I'm looping through it? Am I passing this object by value when it should be by reference? You have to know the life cycle of every variable, when it's born and when it's supposed to die. C++ gives you incredible power, but it demands this incredible level of discipline. And that's really the question to carry forward with you. As these AI tools get better and more common, it's gonna be so easy to just accept code that looks right, that has the right vibe. But the next time you see a piece of C++, I want you to ask yourself, is this just probable syntax, or is it truly memory safe? Because the answer to that question is the difference between a successful program and a silent, catastrophic failure. Thanks for digging into this with me.